Welcome everyone. Today we are happy to have Suhail Dhawan, who is a Marie Curie Fellow at Cambridge. So he's been working on supernovae cosmology, and today he will be given a time domain perspective on the Hubble tension. So welcome and please, when you're ready.
Awesome. Thanks a lot to the organizers for the invite, and thanks to everyone for joining. I'm Suhail, and I'm very excited about measuring the Hubble constant, specifically with supernovae and time domain probes. And the work today I'll be talking about was some that I did when I was ZTF Cosmology Working Group lead, and also some ongoing work with collaborators at the Carnegie Chicago Hubble program, so space-based telescope data analysis. So over the next sort of 40 to 45 minutes, I'll split the talk in two main parts. I'll start with the motivation, why we're so excited right now about the Hubble constant, and moving towards like why specifically these are like the methods to address the tensions currently. So on the right-hand side, you see a plot from the Zwicky Transient Facility first data release of Type 1a supernovae. And that will be part of the first theme of this talk, which is on the local distance scale and measuring h0. In the second part, it will still be centered on supernovae and time domain, but in the strong gravitational lensing domain. So that's the figure on the left-hand side, which is the first resolved strongly lensed Type 1a supernova. And this is HST imaging to resolve the individual images. This is very exciting right now because one, with LSST, we can actually start to think about building a sample of these. And this is scientifically exciting because that's a completely independent probe of cosmology, as it probes time delay distances, which is a ratio of 3 angular diameter distances, compared to local distance ladder, which probes luminosity distances. So before getting into the details of the measurements of h0, like a brief motivation, we have a very well-tested standard model in cosmology. It works extremely well in explaining both data in the early universe as well as the late universe. However, it is a phenomenological model, and there are sort of theoretical problems and gaps, like a physical understanding of the mechanism driving dark energy and what really is cold dark matter. In addition, more recently, with improvements in both statistical and systematic uncertainties, we've seen that there are observational problems that have crept up. And arguably, the most significant of these problems is this so-called Hubble tensions. This is a tension between the inferred value of the Hubble constant from the early universe. So this is using the sound horizon as an absolute distance scale, combined with high redshift probes in the local universe, like Type 1a supernovae and baryon acoustic oscillations, to give an inference of h0 for the standard cosmological model. And this is in tension at the 5 sigma level with the local distance ladder calibrated to Cepheid variables, which is this blue histogram here. Now, this is an end-to-end test of background expansion, so a tension could be a sign of new fundamental physics. However, it could also be a sign of unknown sources of systematics. Therefore, great claims of non-standard cosmology require great evidence, so it's extremely important to go through an entire list of possibilities that it could be as more mundane explanations. There have been some exquisite works in the literature, specifically with the Cepheid distance ladder, looking at unaccounted for sources of systematics, so analysis variance and like sort of obvious things that could go wrong, and they've shown robustly that that isn't the case. But that's still within like the domain of what we know. What is also important is independent distance ladder, so that's this red histogram here. And this is calibrating the supernova luminosity with different independent distances, and we see that is a much better agreement with Planck. So really, independent distance ladders are extremely important to know what is going on in terms of unknown sources of systematics, or systematics that actually hit an error floor when we are looking at these tensions. What's also important is that we should have completely independent distance measurements. So either time delay distances from lens transients, which I'll be talking about in part 2 of the talk, or like completely independent of the local distance ladder calibration through like gravitational wave standard sirens, or even like megamasers. So since throughout the talk, I'll be mentioning the tension in one way or the other, a good cheat sheet is that this tension is approximately 10% in H naught, and when in magnitude space, this is approximately 2/10 of a magnitude. So the full scale of the tension is approximately 0.2 mags. And what I would like to emphasize is that we are comparing to early universe inference from Planck, which has an extremely precise H0 error of 0.5 kilometer per second per megaparsec. So we really need to push to the percent level with local probes in order to be able to sort of say conclusively whether there is new cosmology versus unknown systematics. So since type 1As are going to be a central part of both themes in this talk, just a brief sort of primer on what they are and why they're exciting. So type 1A supernovae have for more than a couple of decades been central to both cosmology as well as end states of stellar evolution. They're extremely bright stellar candles, so they're very good distance indicators, but only when we calibrate the luminosity for the width luminosity relation as well as the color luminosity relation. So they're not standard, but purely based on data-driven relations, we can reduce their dispersion and therefore get precise distances and precision cosmology out of these probes. They were extremely important in the discovery of dark energy, and they are currently also front runners in terms of probes to precisely measure its equation of state and its time dependence. An important part specifically when we're looking at measuring H0 with type 1A supernovae is that they occur in all types of host galaxy environments. There's been discoveries in the last decade suggesting that their distances or inference is dependent on the host galaxy properties. And therefore, when we're using the local distance ladder to measure H0, it is important to have a very precise understanding of the demographics of their host population, and therefore how that impacts our inference of the supernova luminosity. So they're extremely interesting candles with which to measure cosmology, but it's important to keep a check on the systematics that are being propagated through. And what do I mean by that specifically? So just how is H0 measured with the local distance ladder? Now, the luminosity of type 1A supernovae in the nearby Hubble flow, which is this rung in the distance ladder, rung 3, is calibrated with independent distances, in this case, showing it with Cepheids, but it is also calibrated with other distance indicators like the tip of the red giant branch. It is extremely important when making these measurements that between the two contiguous rungs, things are as similar as possible, such that there are no biases between them that are being propagated. So as I mentioned about the host galaxies, we would like that the host galaxy environments out here are as similar to the host galaxy environments out here. Now, this plot, or this slide is showing two different plots, with here the Hubble flow sample is also being used in this case to calibrate or be the low redshift anchor for dark energy studies. And you can see here that this low redshift anchor is built out of lots of different surveys and telescopes and cameras. And the reason why this is a hurdle is because we're trying to get the precision level or percent level estimate in the local distance scale. And having all of these heterogeneous calibrations can be a source of systematic. I'd like to flag that by saying there's been a lot of work specifically with the new Pantheon Plus compilation to combine these together with cross-calibrating them precisely. But again, there's a lot of this information that is no longer available. So it is extremely important to have something that does not have such a heterogeneous calibration when we're trying to get to percent level. In a paper with Dylan Brown and Dan Skolnick, we looked at tying these together, similar to what has been done with Pantheon Plus right now, and essentially going from the calibrator supernovae all the way out to the high redshift in order to be able to infer dark energy and H0 together. And the motivation for that was to see, does our assumption in the sort of high redshift universe impact our inference of the Hubble constant? So previously for the distance ladder, in order to measure H0, we had to assume something about dark energy properties, like what is the value of Q0. Whereas here, we have a simultaneous constraint on both dark energy and H0. We looked at a slew of different models here. We basically were being agnostic to what could be the physical motivation and just seeing, do we get a different value for H0 for any of these? We find that the differences are extremely small, and all of the models are converging to their lambda CDM W equals -1 limit. And therefore, none of the exotic cosmologies in the late universe, including models that have a transition in the late redshift universe, can explain a sizable part of the tension. In addition, there's some work that my student here is leading. We also see that if there were any astrophysical differences between the supernova population in the high redshift universe and in the local universe, they would not be able to explain any sort of transitions that can shift H0 by about 10%. The shifts would be a lot smaller, and this is consistent with independent data like spectroscopy in the intermediate redshift universe. So it shows that late universe cosmological solutions are extremely difficult to explain a sizable part of the tension. So while we looked at this with current data, the aim is, how do we move towards like the precision era, and how can we build an independent, precise distance ladder where we minimize the existing systematics to show whether or not there is actually signs of new cosmology? And to do that, firstly, we need like a precision cosmology instrument and survey. And one of the surveys that I have been working on quite actively is the Zwicky Transient Facility. And it's an excellent discovery machine for supernovae, and it does so in a way that is very different from the literature, with a certain advantage that it is an untargeted survey. So ZTF, just to give a brief overview, is a 47 square degree field of view optical transient survey on Mount Palomar, so on the Schmidt telescope at the 1.2 meter. And it surveys large parts of the sky very quickly, so around 3,700 square degrees an hour. So it can do the entire night sky in 2 optical filters once every 3 days. And that was the strategy for first phase of operations. As I'd shown this plot before, this shows the all-sky distribution of type 1a supernovae from just the first 9 months of operations. This total is around 800 type 1a supernovae. For comparison, at the time, the total low redshift sample, as I'd previously shown you, from all of those different surveys combined was around 200. So we're already like a factor of few improvement. In the second data release, which is imminent in the timescales of this year, we have a total of 3,000 spectroscopically classified type 1a supernovae. So it's an incredibly rich data set, both statistically, but also because it is untargeted. We do not have a pre-selection for which host galaxies we follow the type 1a supernovae in. So we can actually get an unbiased estimate of the underlying environmental distribution. I'll show in the next slide why this is extremely important given the current debates in the type 1a supernova literature. But it's also interesting that beyond just H0 assuming isotropy, this kind of data set is important in order to constrain growth of structure, so like F sigma 8, and can also test the directional dependence of H0. So like, is H0 in a particular solid angle different from that in another solid angle? And this is very important when testing isotropy. It's a fundamental part of the standard model. And I would also like to point out that this very large nearby Hubble flow sample is further complemented by nearby samples that have been observed by ZTF as well. So as I mentioned that you want the second and the third rung to be as similar to each other, we actually have supernovae from the same survey in both of these rungs. That's particularly important because, again, we want to get to precision level. So calibrating one telescope is a comparatively lot easier problem than trying to cross-calibrate multiple ones. So the reason why this untargeted survey is a very crucial part of the survey strategy is because there's a lot of debate in the literature about how the supernova luminosity depends on its host galaxy properties. It has been seen for around the last 10 to 15 years that the supernova luminosity depends on the host galaxy mass. That is, that those supernovae that are in more massive host galaxies are on average a tenth of a magnitude brighter after their standardization corrections. Now, the puzzle here is, why should the supernova luminosity depend on its host galaxy mass? There must be something that is a more precise tracer of what is driving this correlation. And secondly, why should it depend on a global property? Like, why should the supernova care about the global properties of the galaxy? So what people have looked at is, does this depend on local properties like specific star formation rate, so star formation rate per solar mass? And what has been found, and this is quite debated in the literature, is the extent to which the specific star formation rate step is impacting the inference on H0. So in some cases, people find that the difference between the young and the old star environments is quite high, like of order 0.1 to 0.15 mag. Again, the cheat sheet, like the size of the tension is 0.2 mag. The reason why this impacts a lot is because Cepheids are only in this part of the specific star formation rate distribution. They're specifically in young star forming environments. However, if the effect is a lot smaller, then this should not impact H0 by more than 1% at max. So this is why having an untargeted sample is important, because we don't know what the selection effect is that goes into the x-axis. So it's very difficult to say whether or not there are selection biases that are impacting what we infer about this specific star formation rate step. So in this case, ZTF has been a great discovery machine. So this is a plot from the first data release paper. Details are in the reference here, but I'm also very happy to talk about this offline. We see that the host galaxy mass distribution is a lot more evenly spread between the low mass and the high mass events compared to the literature, which is the green histogram. This shows that this untargeted search is actually finding a lot more supernovae in the host environments that were previously not probed by the targeted searches in the literature. We also have a much larger statistical sample with which we can look at sub-selecting mass spins and comparing the Hubble residuals to see how that compares to the literature sample, but also within each other to see what is the level of this step. In addition, the ZTF sample has an exquisite set of light curves where the first detection, because of its very large field of view, is around a couple of weeks before maximum light. And this is compared to the literature where it's only a few days before maximum light. This is particularly important because the distance scatter can then be improved significantly, as has been seen in several studies in the literature. But there isn't a significant statistical sample before ZTF that has been able to do this in a way that can be used for cosmology. So the ZTF sample already can retrain the distance calculation model such that we can further improve the scatter even based on the first 9 months of data. And that's something that's super exciting and is ongoing work within the collaboration. Moreover, the ZTF sample also pushes to a higher median redshift, and that means that it's less prone to systematics from peculiar velocity uncertainties. And that's something that's, again, important when we're looking at a complete error budget that is getting to the percent level. So as I'd mentioned previously, the way in which to measure H0 is to calibrate the distances of type 1a supernova in the Hubble flow with independent distance measurements to host galaxies in the nearby calibrator sample. So rung 2 of the distance ladder, known as the calibrators, and rung 3 is the Hubble flow. For this, we need independent distance indicators. Cepheids have been used very well to get to the precision level that we have right now, but they do have certain sort of astrophysical systematics that would need independent checks of. So they exist in very crowded regions in young star-forming galaxies in their disks, whereas the tip of the red giant branch, which is an independent distance indicator, is in a lot less crowded environment towards the halos of nearby galaxies. And they're found in supernova hosts of all ages. So whereas Cepheids are specifically only in the young star-forming environments, as I previously mentioned, the TRGB is actually in all host galaxies. And therefore, we can actually test whether or not this astrophysical bias is something that is a dominant aspect of our error budget. They're also less prone to reddening and metallicity, as well as like crowding biases, because they're out in the halo, so they aren't as impacted by this cut as the Cepheids are. Complementarily, TRGBs are also fainter, so we do sort of need to use much bigger telescopes. So this is something that will be more important in the GWST era in order to push to the same volume. So the reason for looking at ZTF with TRGB distances is that ZTF probes the entire underlying host mass distribution of 1As, but Cepheids as calibrators would not. TRGBs would span the entire range. So in order to have the calibrators and the Hubble flow in as similar an environment, we really need to have a probe that has distances that we can be measuring in both young and old host galaxies. So we started looking at this program with HST data for calibrating the host galaxies of nearby 1As measured by ZTF. And what we found is that while the TRGB with HST is still in like a small volume, so only around 25 megaparsec, where we don't have that many galaxies that have hosted supernovae, we have around 6 type 1A supernovae in that volume with very good supernova data in multiple filters. So an example of this is the supernova 2021 RHU that we published early last year. It has excellent rise time coverage, and it also has a lot of late time coverage in multiple filters. This is something that's extremely important because in this case, we can retrain the model because we see that there's a lot of important features in the late time in the redder filters that the current Sol2 model is not doing a good job of representing. But at the current moment, out of these 6, there was only 1 that had archival data. So this was a proof of concept study, so which is evident in the error bar in H0, which is just a single object. But we looked at lots of different analysis variants, like differences in sample selection based on the Hubble flow redshift, differences in the supernova light curve fitting method, and we don't find that that has a very big impact currently compared to the total error budget. We see that like if we go from the calibrator to the Hubble flow with everything on just the same photometric system and same instrument, we can actually get uncertainties on H0 per calibrator that are the same as in the literature, and in some cases like even slightly better than some of the well-sampled supernovae in the literature. So it's a good proof of concept showing that this can really be done even with archival HST data. And now we've proposed for getting and increasing the sample to the total of 6 type 1As that are there in the volume. So we'll be able to very soon reduce this error bar by √n, which is going to be very exciting because even with HST, we can then start to get to the few percent uncertainty. What's also extremely exciting is that since the TRGB is a probe that is bright in the infrared, we can push to much higher volume. So this volume is up to 80 megaparsec, which is the sensitivity of NearCam on GWST. And with an increased Hubble flow sample of 3000 type 1As, we can further reduce the uncertainty, both because of having a larger number of calibrators, but also we can start to test whether or not there is astrophysical bias by specifically targeting elliptical galaxies, so old stellar populations, so that we can measure H0 just from ellipticals and compare that to what we have in the literature from Cepheids and see whether or not there is an agreement. So we have a cycle 2 proposal that is currently been put in to see whether or not there is signs of environmental systematics, or if there is agreement between the ellipticals and local Cepheid measurements of H0. That would be a very strong sign pointing towards non-standard cosmology as a solution. So in the second part of my talk, I'll be mentioning the use of supernovae in the strong lensing regime, but I'll pause for a bit for questions right now because that's a little different from the local distance ladder. So if there are questions, I'd be very happy to take them now on this part of the talk.
Yeah, Joby, please go ahead.
Yeah, so could you explain again what allows us to go, like, use calibrating samples up to 80 megaparsec?
Great. So
Yeah.
So at this point, it's that JWST just has higher sensitivity in the radar filters. So we can just go much deeper in magnitude. So that gives us a much larger volume compared to HST.
This is using TRGBs?
Yes, that is right.
Oh. But if we use Cepheids, we are still limited to like 40 megaparsec.
So that's a very good question. The thing is, Cepheids are periodic variables, so you need multiple epochs of each host galaxy. And given JWST's size and slew time and jittery, the overheads are extremely high to do like time domain with JWST. So if you get with TRGBs, you'll get it all in a single shot, whereas for Cepheids, you need multiple epochs to get the period.
I see. Thank you.
Okay. Awesome. So if there aren't other questions, in the second part, I wanted to talk about some recent work that we've done on lens supernovae. So this is using supernovae, but in the strong lensing regime in order to again measure H0, but is also exciting for lots of other science goals. So in GR, for certain favorable alignments of source and observer and an intervening object, we can get multiple images. And if that transient source, if that source is a transient, we actually have very defined epochs in the brightness evolution. And using the difference in the arrival time, we can actually infer H0 if we have a model for the lens potential. So that's just this equation down here. And it's a very sort of simple idea that was proposed by the Norwegian astronomer Sjur Refsdal in 1964. So it's quite an old idea, but it has been used for quasars a lot more because they are a lot more abundant. Lens supernovae are rare events. But however, we find that like supernovae, which require only like a few weeks of monitoring, are a lot easier to get robust time delays for compared to stochastic light curves for quasars, which have required years of monitoring in their observing campaigns. Also, supernovae specifically of type 1a have a standardizable luminosity. So we can break modeling degeneracies like the mass sheet transformation, which has been a systematic that has been shown for H0 measurements with lens quasars right now. Also, because they have well understood SEDs and light curve models, and we have seen with simulations, they have a much lower impact of microlensing systematics, which is really important, again, when we want to use a small sample of lens supernovae to try and get to precision estimate in H0. So we were part of the team that discovered and followed up the first resolved lens type 1a supernova. So in this case, that what is very exciting and what trying to show here with the image on the left-hand side is that the Discovery mission, which was the intermediate Palomar transient factory, so ZTF's predecessor survey on the same telescope, has a very poor resolution. But because we know the intrinsic luminosity of type 1e supernova, this supernova, when compared to its sort of analog at the given redshift, was around 50 times brighter. So just fitting the standard template, we got a much higher brightness, like almost 4 magnitudes brighter than what we would expect for a 1A at that redshift. Now, being such a strong outlier and being at redshift 0.4 discovered with a 1.2 meter was something that was suggesting that lensing could be an explanation, and the spectrum looked exactly like a 1A at redshift 0.4. We got follow-up from bigger telescopes such that we could then see both the spectral lines from the host and the lens galaxy, and then got follow-up from HST. So what this is a very complementary approach to looking at image multiplicity, and this doesn't require high resolution, so we can do this with wide field surveys like ZTF and LSST in the future. The other interesting thing about the lens supernovae is that they fade away, unlike quasars, which are persistent sources. So in the template, we actually only get the host and lens. So we can actually have a complementary check of the lens model without the transient source in there. The light curves here are going from the UV to the IR. So we got multi-band imaging for in multiple epochs for the supernova. It's an extremely small time delay because it's a very symmetric configuration. So it's not an ideal case for measuring H0. But with the multi-band imaging, we can constrain a lot of properties of both the supernova as well as the intervening material in the host and the lens galaxy. So we can put extremely tight constraints on dust properties in each individual line of sight for the 4 images. So as we see that in typically what we would expect in the lens modeling is that if it's a very symmetric configuration, the flux ratio should be close to unity. However, as we can see from this image, like image 1 seems a lot brighter than, say, image 4. And could this be because of differential extinction? And we tried doing that, and we found some part of it can be explained with differential extinction, but definitely not all of it. What we find is, despite the differential extinction, from these observed histograms, we can see that image 1 is a lot brighter than images 3 and 4. So what was a possible explanation is, when comparing this to stellar networks, which have a full microlensing map, that a magnification of image 1 and a demagnification of images 3 and 4 on top of this differential extinction could be a likely explanation for these different brightnesses. So there's a lot of interesting science that we can do about like extinction in the line of sight, where we can see that these highly extinguished images are not having similar dust laws to our own Milky Way. Or we can also like use the magnification after extinction correction in order to probe the different predictions of amplification distribution from different exotic theories of gravity. The flux ratios can also be used in order to infer potential compact object sources of dark matter, and that's something that we are currently exploring, but like details of the lens modeling and the microlensing maps are in Edward Motzell's paper. So there's a lot of non-H0 interesting science that we can do with this, both with extinction as well as flux ratios and the total magnification. One thing that's really interesting is that while with the unresolved data in just a single filter, we thought that this would be around 50 times magnified. When we actually account for the fact that these images are extinguished, the inferred magnification is a lot more precise and a lot higher than what we would expect. So in order to precisely constrain the lensing magnification in a model-independent way, we need the multi-wavelength follow-up. And it's really cool to see that like we can constrain it to such a precise, like almost 5% constraint on mu, such that we can then build an amplification distribution. In the follow-up to IPTF, so with ZTF, we've been looking for lens supernovae systematically for the few years of its operations. The expected rate was low, but in the summer of last year, we found supernova Zwicky. So this was found again in the low-resolution imaging of ZTF. We triggered the VLT to get better resolution IFU spectroscopy and infrared photometry, as well as triggering the Liverpool telescope, because this was extremely bright, in order to get multi-band follow-up and constrained properties like the extinction, but also the time delay. As you may now be able to see from the previous image of the supernova IPTF 16GU, this very symmetric configuration again suggests that the time delay is not very high. But we can learn a lot about the supernova from the spectroscopy, as well as model the lens galaxy and get a lot of interesting stuff about the lensing system itself. What was really interesting is that this was an extremely compact system with an Einstein radius that is below 0.2 arcseconds. So we can study the central stellar IMF with such systems. And these would be extremely hard to discover with image multiplicity, because that would require monitoring with very high resolution, very sort of time-intensive data. And in this case, we can actually discover them with the candle behind them, which has a very well-known and well-understood luminosity. So this is why we could clearly see a lensing signal. This is what we would expect as the 1 sigma distribution of a 1A, and this is where supernova Zwicky was. In addition, as I mentioned, the spectroscopy in and of itself is something that is very useful, because this is an extremely high signal to noise data set of UV to optical spectra of type 1a supernovae at redshift 0.35. So we can really see like supernovae with a look back time of 4 billion years with like the same level of precision that we would see local type 1a supernovae, and that's thanks to the 3.5 magnitudes of extinction. So there's the use of the gravitational telescope idea from Zwicky that is to study the high redshift sources a lot better because of the boost that we get from the lensing magnification. So this is some ongoing work being led by Joel Johansson that I'm involved in, which is on studying the spectral time series and comparing it to the low redshift. And this is very powerful because comparing low redshift to high redshift properties is extremely important to see whether or not there are any subtle systematics in the progenitor evolution that can potentially impact dark energy inference. We find currently preliminarily that none of the spectroscopic features seem any different from the low redshift sample, and that's suggesting that this evolution is probably quite small. So we still can't rule out the scale at which this would be impacting, say, W measurements, but it's not something that looks very different from the nearby universe. In addition, something that I'm leading currently is that there's a JWST Cycle 2 proposal to do late-time imaging and spectroscopy in order to understand the progenitors of these 1As at high redshift. This is something that's very cool because nebular phase observations, which is actually looking at the core of these supernova explosions, are something that can only really be done at very, very nearby distances, like below 50 megaparsec. Here we can start looking at it at like a look back time of 4 giga years. So being able to do that is something that's possible because of both the capacity of Webb to go as deep as like 25th magnitude, which is what we need for supernova Zwicky, but also would not have been possible without the magnification boost that we get from lensing. So that makes this an extremely interesting system to study both the supernova properties as well as the lensing properties, even though it is extremely compact and we can't use this for like very precise H0 measurements. However, like this is super promising because it's actually showing that lens supernovae going from just an idea to actual discoveries that are happening with wide field transient surveys today. So as we want to now move towards precision estimates in cosmology, the most impactful discovery machine would be LSST in the near future. Some work that done with Simon Berger was on seeing how many supernovae we need to get to similar precision on H0 with lens supernovae using LSST. So we found that for a few tens of lens supernovae, we can get to similar precisions to the local distance scale. And again, given that it's completely independent, that is what we would need in order to test whether or not there's an agreement with the local distance scale estimate of H0, and therefore is it suggesting the possibility of new cosmology, or is it agreeing with the early universe and therefore suggesting maybe there's unknown systematics. We've also done realistic simulations of the LSST cadence. So this is saying we do need this for H0, but can we really find it? So this is with extremely realistic and precise simulations of LSST's observing strategy. And we find that despite which kind of observing strategy we have, whether it's uniform across the sky or repeated measurements in patches of the sky, we would expect a few tens of supernovae per year, and that would be sufficient in order to give us the sample for H0. We also do certain follow-up tests on will we actually be able to do this in real time, and we find that for a sizable subsample of this, we can actually build the sample very quickly in the first few years of LSST observations. So that is a promising sign for actually building the sample up. And some work that I'm doing with Justin Pirel, which is on trying to actually infer these time delays extremely precisely, because these supernovae, we need like very prompt follow-up. So we're working on sort of what is the best synergy between LSST and space-based follow-up, like with HST and GWST, to use those precious resources well in order to constrain time delays at the few percent level. And that's some ongoing work. So we're very excited to see how that synergy goes across. So I'll put up my conclusions on what the current status is on using both supernovae in the local distance scale and strongly lensed supernovae to measure H0. So yeah, thanks a lot for your attention, and very happy to discuss more and take questions.
All right, thank you, Suhail, for that very nice talk. Are there any questions? Yeah, Yogi, go ahead, please.
So, do you have an estimate of like roughly how many supernovae, strongly lensed supernovae, do we need to get like a 1.5% H0 measurement?
Yeah, so that's what we looked at in the paper, was that each supernova is approximately like 7 to 8% on H0. So a few tens would be sufficient in order to get to this precision level.
And do we expect that maybe JWST or so will be able to get these like tens of lengths?
Yeah, so that was in the last part, what I was mentioning was that with the LSST, because we need wide area, we expect that this is per year number of lens supernovae. So we simulate like a survey. We put the lens supernova sources there, and we say, okay, if it has all the problems with the weather and telescope downtime and things like that we've simulated, we still expect that we'd get a few tens per year which have good enough light curves that we can actually in real time say this is interesting as a lens supernova, then get a spectrum and confirm it, and actually get the follow-up to get time delays. So the numbers look that like we can actually do this. So with a few years of LSST, GWST would be great to both find them, say, in clusters, because it'll be staring in clusters as well, and also to get follow-up. So LSST will not have the resolution to get, say, these individual images, but GWST will. So the aim is find them with LSST and then observe them, the golden sample with GWST. Yeah.
Oh, I see. Very exciting.
Yeah.
Thank you.
Are there any other questions? If not, I have a few myself. So Maybe you mentioned it, but it's not clear to me in the first part of the talk. You mentioned this mass step and star formation rate, and how it is a problem to essentially select the ones you're going to use for H naught. But so how does ZTF improve this? I mean, the fact that it's untargeted, or how?
Yeah, it's essentially that, but maybe I can say, yeah, it's essentially the fact that so when we see plots like this, typically there's one survey that finds the supernovae, and then like you get a spectrum, and like what we have like follow-up telescope, which may be doing a large sample, but like there's always going to be like a selection effect associated with the follow-up, like maybe don't follow the highly reddened ones, or follow them only in like a certain set of target galaxies, for example. Whereas one of the things is that with ZTF, we're doing discovery in each batch, and then like because ZTF goes back to the same spot every 3 days in G and R, and in the I band goes back every 4 days, we build these kind of light curves like without follow-ups. It's with the same, like this, the first point of discovery is with the same telescope as all of the other data. So it doesn't there's no sort of selection that comes in because of like picking which supernovae to go after. We can actually get the full host galaxy distribution. So the green histogram is showing the low mass end, which is underpopulated in the literature, whereas like we actually get like the blue histogram, which is almost equal between like the low and the high mass. So that's why we can actually get everything that's in both the young and the old stellar populations, because we have it as an untargeted survey and classify everything.
All right, I see. I have other questions, but maybe I can ask again. Is there any other questions from people in the audience? Okay, so I'll ask again. So for this anisotropy test, because I think you at some point you said that we expect 3,000 supernovae with ZTF. How many do we expect? Is there any forecast on the very low redshift regime, or I mean, how many of them would be used for full testing anisotropy?
Yeah. So I might have a backup slide on this where so yeah, so okay, there's lots of contour plots, but so this is the DR1 sample, which is around 800. There'll be 3,000 in DR2, and if we assume like that, so this is like anisotropy is in this case, like this is a small forecast that we did for ZTF with the eigenvectors, the quadrupole. So this would be lambda CDM is just 0, 0. And we find that with 3,000 supernovae, we would be able to test at least at the 6 sigma level what the like the difference between the case, which is like say a few percent anisotropy, and lambda CDM. So this is a forecast. So this is assuming that there is an anisotropy. How well can we test it? So with that sample, and that's like 3,000 good type 1As with good distances and that pass the selection criteria. Likewise, like if it's a true cosmology, like if it is actually isotropic, we should be able to like rule out these well motivated few percent anisotropies at a similar significance. So that would be the sort of gold sample to test the even the smallest of well motivated anisotropies.
I see, and I guess that this is all for the DR2 release, right?
That's for DR2. That's right.
And
so
when is this expected to come?
I think by the end of the year.
Oh, okay. Oh, yeah. Nice. Interesting. Are there any other questions, Ben?
I just have a short follow-up question on this. So how do you come up with your expectation on the anisotropy in the Hubble parameter?
Right. So we essentially we use a model-independent approach, which is like a cosmographic expansion, but it is actually directionally dependent. So this h of E is basically the Hubble parameter as a function of direction. There are many different ways to do this, but like we take this sort of model-independent eigenvector approach to look at the quadrupole, and we look at these quadrupolar signatures by like fitting the low and high redshift data together with a certain decay scale, and then constrain lambda1 and lambda2. So these are the constraints that we get from Pantheon Plus, because that's a well-calibrated sort of, it covers a large part of the sky sample. We see small deviations from isotropy, but like with how heterogeneous the sample is, like we won't claim anything significant. Anyways, it's even statistically just 2 sigma. But basically we like use this Hubble parameter expression and like simultaneously fit high and low redshift data. Yeah.
All right, thanks.
I think Christoph and Arman.
Yes, so it's more a technical question. What physical processes drive supernovas to be different in different galaxies or environments? What's the motivation behind this?
Oh, nice. So this is a great question, because it's quite an interesting open question right now. There could be 2 explanations, and likely a superposition of both. A 0.1 mag step could partially be because of, say, difference in dust properties, like the R sub V, the slope of the dust law in low and high mass galaxies. So like we could say that the star-forming ones are going to be dustier, so we could have steeper dust laws, and that can, like, if you fit everything with a single dust law, then that might show up as a residual step. Now, there's debate about whether that's dominant, or whether like there's local properties, like could there be secondary effects in the progenitor, like metallicity, the presence of neon 22, that is essentially leading to intrinsic differences in the luminosity. And given it's a bit difficult to test the intrinsic part at high redshift, it's also difficult to test the dust part, but maybe also difficult to get, like, say, spectroscopy time series at redshift 0.5. There's a debate about what the relative effect of those 2 causes is, but that's broadly the reasons that would be driving such a step.
Thank you.
Arman?
So, okay, can you go back to your isotropy test?
Yeah. Yeah.
Okay, so what do you mean by model independent?
Right. So essentially, like we just take like simulations that have been run with no assumption on the A of T. So this is Asta Heinessen and Haley McPherson's papers that have been looking at which are the dominant higher order multiples. And so more detailed analysis is also done, like, by one of my students, like Jess Cowell. In this paper, I can point you to that, like, to basically say which of the higher order multiples is dominant, and then doing model independent in the same way that, like, we don't assume like an anisotropy in, say, omega lambda or something specific like that. Like in a similar way to, like, we do isotropic cosmography with Q0, J0 and higher order terms, we do like anisotropy with the highest the multiple that has the highest power in H0, Q0, and like we find that, like, there's no expected anisotropy in J0, but yeah, so we done it with like a quadrupole in H0, and in other cases, like has been done in the literature with a dipole in Q0.
So still you assume a kind of particular framework, right? So going to this different modes of anisotropy, basically, right?
It's true, yes. So it is like,
So that's what I'm calling it, that, calling something model independent is maybe, I don't find it maybe completely appropriate, because, you might have, for example, isotropy is clear, but anything which is not isotropic is anisotropic, right? And it is not something new, right? So you can have basically like a very small patch of the sky which has some anisotropic properties, which could be primordial, which could not be primordial. It could basically happen anytime in the cosmic history. And such methods may not be even sensitive to that, because they are sensitive to a particular form of anisotropy.
That is correct. That like I do agree that like if we were to find a signal, it would be sort of very intensive to explain its like primordial or origin, or like what its origin is. And I think it's model independent within a cosmographic framework. So we think this is an interesting method, but I agree with, it's not an exclusive way of finding anisotropies. We could just as well like bin stuff in solid angles and get like H0 in each one of them and just compare that and see whether or not there are any deviations there. That could just as well be another way of quantifying whether there are anisotropies. One of the things we're looking at right now, which is if we have a few different frameworks with which we want to quantify anisotropy, how does our like survey selection and like how do the regular supernova systematics impact that? And for that, we're actually looking at this method, but also like both more simple and more complicated methods of quantifying anisotropies. So it's true when we say model independent, I mean more like within a cosmographic framework.
Okay, yeah, thank you.
Any other urgent questions? We're slightly over time, but we can have one probably short question. If not, let's thank Suhail again, and we